Welcome to today's webinar. The topic today is force finding of cable tensile structures in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and PR. For example, the German and English webinars. I will be the moderator today and I will answer your questions during the webinar. My colleague Clemens Gutmann will be the presenter today. He's responsible for customer support and product engineering. And for example, also responsible for the add-on form finding. Okay, how you can ask questions. At first, I switch off my webcam that you can see the full screen. When you would like to ask a question, then press that button with the question mark here. Then you can enter your question in that field, press send, and I will receive your question and I will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's at the moment all from my side. I hand over to Clemens. Clemens, it's your turn.
Yeah, thank you, Andreas, for the introductory words. And I too want to welcome you to today's webinar. Today I want to show you how to perform force finding by using our add-on form finding and RFEM 6. So usually the add-on form finding, by its name, is used for performing form finding. But I want to show you that you can flip this process around and you can find a force for a given geometry instead of finding a geometry for a given force. And the principles I'll show you with a simple cable net structure, and later on we are going to have a look at a more complex structure that is shown on the right. So I imagine myself being a civil engineer and an architect comes up to me and says, well, I designed this cable net structure, which is supposed to be a climbing frame for children, and I ask you to construct this. So you have the task now to find the right pre-stresses for this cable net structure so that the shape and the geometry stays put and it maintains the shape like the architect wants it to be and as he designed. So yeah, this is the scope, and let's go into the software and have a look how to do this. At first, we need to create ourselves a new model. I'm going to name it simple cable net. And I'm going to deactivate surfaces and solids as I don't need them. And that way the data navigator becomes a little bit clearer. Additionally, of course, we need the add-on form finding. Okay. We then proceed with the modeling, and my simple cable net shall consist of a arch with a gauge of 1 meter and a width of 10 meters. I then want to mirror this about the XY plane and the center point one time. Sorry, made the mistake. Forgot to check the copy option. And these two arcs I want to connect by straight lines. And those straight lines I want to copy with a distance of 1 meter in either direction. So 1, 2, 3, 4 times. And 1 meter, hit apply, and then again in the other direction. And I want to connect those straight lines now to the arches, and there's a quite handy way to do this. There's an option that has not been too long available in the software, and that is the extend graphically command. There's the opposite command as well, the trim graphically. It does the same, but the other way around. So if I click on it and hover over the end of a line, it automatically searches for other lines in that plane and creates a preview where an intersection has been found. And if you click on it, the intersection has been made and the line is extended to the other line. And that way, complex intersections can be made quite easily and fast. I want to connect all those lines, so I get small chunks of the between the straight lines, and I proceed with the material. I want to use a cable material from Fatsa today. Okay, and a section, a round bar section with 10 millimeters diameter. I then want to assign this section to all the lines I've created, and of course the member type is supposed to be cable. Select all lines. Okay. And okay. The colorful squares you see is an indicator that member representatives have been found. This is quite a handy feature if you want to design a structure. So the software searches for members that have the same property and the same shape and groups them together in a so-called member representative. But since I do not want to perform a design today and every member is different, I deactivate this in the display navigator. Next step would be to assign a nodal support to the corners. Let's make them a little bit bigger. Okay, and now we can define our load cases. Today I do not want to use the self-weight for this model, but just a pre-stress load case. And there's another setting that we have to adjust, and that is the something in the static analysis settings. So I'm going to edit those. And if you activate the form finding add-on, you get a new tab for the add-on here. And there are 3 options that I'm going to explain to you very quickly. So the number of iterations for loading pre-stress determines how often the form finding solver tries to find a solution for the boundary conditions that you gave to him. So if you define form finding loads, either force loads or geometry related loads, those are boundary conditions for the form finding solver, and he tries to find a solution that matches the boundary conditions the best. And usually if you perform form finding, 15 is a good number, but since we want to do a force finding and we want to get a very exact result, I'm going to increase this number to 60. Depending on what model you want to force find, you have to try out yourself what number fits best. At a certain point, if you increase the number further, it will not result in a better result. The second option is the speed of convergence. This is a setting where you can influence the stiffness of the members and the membranes. So this is especially interesting if you have structures with large deformations during the form finding process. So if the number is lower, the structure moves more slowly through the space, and it can result in a better convergence if you have large deformations. But usually the default value of 1 is totally fine. But if you have some issues, remember that this option is existent and try if it helps. The third option is the integrate preliminary form finding. If you activate this option, there's another step being performed before the form finding solver is activated, and there's a form finding method called force density method. And if you check this option, this method is used in a first step to create a approximate form finding geometry, and this is the initial state then for the form finding solver to build on top of that the solution. So this is also very interesting for structures that have large deformations during the form finding process. So since we do not want any deformations, those last two options are not for us today, but I still wanted to explain them to you. We click OK, and again OK. Now we can define our member loads, and for this I'm going to use the load type form finding, of course. And at first I want to create an average force and member definition for the member in the center. It's going to be 1 kilonewton, but as you may know, with form finding, it's actually irrelevant what size you pick. What matters is the ratio in the different directions. So you could also pick 10 or 0.1 or 5, whatever you like. It's just a reference for the form finding solver to find the pre-stress level. Okay, we click apply and next. And to all other members, I want to assign a geometric form finding load with 100% length. So I want that all those members maintain their length. And I'm going to assign those to all other members. Okay, and okay. Now we are ready to calculate this load case. And let's have a look at the result. The result is not as good as I hoped, and there's a specific reason for this. So since the force finding method of sorts derives from form finding, it is impossible to force find a structure that cannot be form found. And in our specific case, the arch is it has a little gauge, the small chunks of it, and if you apply attention to those chunks, it's going to be rectified, of course. And this is the deformation we see here now. And this deformation accumulates in the middle, and that's why the deformation is the biggest in the middle. So to correct this, I'm going to delete those arches and connect the points with a straight member. So I'm going to select continuous. And tick all the nodes. Okay. And for the bottom, I'll mirror this again. Before we can calculate, I need to assign the loads again to the new members. Okay. And let's try this one more time. And now we get the result that we've expected. There's almost no deformation. It's, neglectably small, and we get a normal force layout that is reasonable. We have the 1 kilonewton in the middle, and like a hanging bridge, a bigger normal force in the arched cable members. And to show you that this is a real result and that the form finding solver did not imagine something, I want to validate this result. And in order to do that, I wrote myself a little Python script that is reading the result data of the load case 1. Then I filter the result data in order to get the internal normal force. And I want to assign those normal forces then as an initial pre-stress to the members in a load case number 2. And I have to create a new load case for that. I'll call it pre-stress validation. I'll leave all settings the same. Click OK. And now I can execute this script. I have to change the model name. Simple CableNet. And click OK. This takes a short while. So now the script contacts RFEM, and we're going to see that the program is locked now through the script, and the script is going to perform the steps that I've explained, and now the software is unlocked again, and we can proceed with the analyzing this model. So let's check whether the script has performed correctly. So we have 13.84 here on the left and 12.99 in the middle. And if we go to the load case number 2 and have a look at the loads, we can see those values on the left and in the middle. So that worked out. And these loads, as I said, are of type initial pre-stress. So this is a member load. It's not a form finding load. It's a member load, and it's the initial pre-stress for the member. And we're going to see whether this initial pre-stress is also going to be the final pre-stress of the member by calculating this load case. And as we can see, the result is very, very nice. We get as a final result the same what we put in as a load. We can have a look at the global deformations, and those are even smaller than before. So the form finding solver found a valid and good solution for the boundary conditions that we gave to him. And there are no global deformations, and we found the force that is needed as a pre-stress for the structure in order to maintain its shape. We want to proceed now to the more complex structure, and therefore we are going to create as a new model. And I'm going to name this climbing frame. And again, we need the add-on form finding. And since I want to import the .exef file that I've got from my architect, I want to flip the global axis because usually drawings are with the z-axis pointing upwards. And now I can go to File, Import .exef, and import the .exef file that I got from the architect. And yeah, the import has been successfully performed. And as you can see, the structure, the geometry is a lot more complex. And let's check whether it is correctly drawn with a quick model check for identical numbers, none, and overlapping lines, none. That's good. Now we can proceed with the material. I want to use the same materials as before. So this cable material and the round section material with a diameter of 10 millimeters. New member, again cable, and assign this to every line individually. Yeah, this is even more colorful with the member representatives, so I'm going to deactivate those again, as I don't need them as well here. Next step would be again the support, and the substructure usually consisting of some columns and a circular section. I do not want to model today, so I'm just going to hold all the corner points. Okay. And okay. Looks good. And for the pre-stress load later on, I want to parametrize this to show you the influence of the pre-stress level. So I'm going to define myself a new global parameter, and I'm going to name this pre-stress level, and this is going to be a float value, and let's start with 0.1 or 10%. Hit OK, and create us some loads. I want again assign one form finding load of type force with now parametricized force. So I'm clicking on that right arrow here and select the option Edit Formula. And I want the pre-stress level variable that I've just defined times the section area of the cable. So I'm typing in sections, and my cable has the section number 1, and I want the area of this, and I want to multiply this with the yield strength of the cable, which is usually 1770 MPa. So usually the formula editor reads the SI units, so newtons, meters, kilograms, and so on. But you can tell him that it is another unit by just typing MPa. So yeah, now he gets that this is a different unit and calculates the value accordingly. We click OK, and now we have a yellow triangle in the top left corner, and this indicates that this value is a result of a formula calculation. And I want to assign this to a member that I know that is going to be under a lot of pre-stress, and I assume that those are going to be the edge cables. So I'm going to pick this one right beside the support. Apply, and next. And I want to assign to all other members again the geometric definition type of 100%. Select all. You notice that it, although I selected also this one member, it's not selecting it because you can only define one form finding load to a member. There cannot be two boundary conditions for the form finding solver for the same element. So yeah, this is why. Click OK, and OK. Good. Now let's go to the load cases and combinations. I again only want to use a pre-stress for now and deactivate the self-weight and make again some changes to the static analysis settings. And now I want to show you how what the influence of this form finding iteration number is on the result. So for the first calculation, I'll leave it at 15. Then I want a second analysis setting with 75, and then 150. And we'll take a look at what affects the result. Let's calculate everything. And have a look at the results. So we have, not that large, but still significant deformations of almost 20 millimeters. And this is due to the fact that the number of iterations is set too low. So let's try again and assign the second option with a 75 iterations and calculate the load case again. Now we can see that the result has gotten a lot better. We have a almost negligible size of the deformation, and let's try one higher number with a 150. So let's remember the 1.8. Calculate this again. So as you can see, the result got a little bit better, like 1 decimal place roughly. And you have to think for yourself if this is necessary that you have this improvement. So for me, I think the number of 75 is sufficient, and we can save some time if we limit the number of iterations for the form finding solver here. Good, so let's calculate the results again. Did not save that. Okay. And another thing that I wanted to show you was the influence of the pre-stress. So if you take a look at the normal internal forces, we have here the 13.9 that we predefined earlier. And I'm going to change now the global parameter to 50% and click OK. Let's calculate again. And as you can see, of course, the number has increased, but it is still the predefined value of 69.51. And if we take a look at the global deformations, the value of the global deformations has been is lower than before. That is due to the fact that a higher pre-stress yields in a higher stiffness of the geometry, but as you can see, the influence is not significant. With this model, I also want to show you the validation of the result. But since this is this model has more members, it takes some time for the results being transferred into the new load case 2, like before. So I prepared another model where we already have those results, and I'm going to open this now. So let's have a look. I have created a new load case number 2, like before, and the initial pre-stress loads are the same as the results of load case number 1. So we have the 69.51 in load case number 2, and this is the result of the load case number 1. So result values here. So this is the same. So let's calculate this and see whether the deformation changes or whether it stays the same. And as we can see, the deformation is good. It's neglectably small. And so again, the form finding solver also found a valid and good solution for the given boundary conditions for this complex structure. Let's go back into our original model. And yeah, I said that I deactivated the self weight, and I want to show you what effects derive from activating this option. Calculate. And like I said before, you are bound to the rules and laws of form finding. So because we have at some places a very small stiffness in the global Z direction, there are some notable deformations in terms of civil engineering, still quite small with less than 2 millimeters, but still there are limitations, of course, physical limitations to the force finding method. But still, I think this is a good result, like a practical result. And let's see what the structure, how the structure reacts to a child load. So usually, let's pick none. Usually you have a man load, but since this is a climbing frame, I'll apply a child load to this. And I want to consider the pre-stress load case as initial state for the calculation of this load case. And let's apply some node loads of maybe 0.5 kilonewtons to some nodes here in the model. So maybe a child is up here, and maybe another one down here, and over here, and maybe over here. Okay. Let's check out the results for this. And as expected, the deformations get higher. And yeah, this is due to the stiffness of the cable net in that direction. But still, I think with less than 20 millimeters, the deformations are neglectably small. But let's see what the level of pre-stress, sorry, wrong button, level of pre-stress, has which effect does the level of pre-stress have on the result. So let's go back to only 10% pre-stress level and see which deformations we get now. Okay, we got an error. That is due to the fact that the number of iterations for the calculation is set too low for this model. So let's try again with the higher number of iterations. So the solver has some more time to find a solution. Okay, just a little bit more than 100. Okay. Didn't calculate the second one. Let's do this again. All right. So for the pre-stress level, we have the expected results, or closely. And for the deformations with the child load, we can see that the deformations have gotten significantly larger, with almost 60 millimeters now. Still, I think okay, but yeah, of course, there's an influence of the pre-stress level later on, not for the form finding, but if you use the form found and pre-stressed structure for additional loads, it makes a difference what pre-stress level you have applied to the model. And this is all I wanted to show you today. And thanks for watching, and I'll give back to Andreas now. Thank you.
Thank you, Clemens, for your presentation. I have an additional hint. You can book our new online courses. For more information and the prices, you can click on that links at the bottom, or you can scan the QR codes. That's the RFEM 6 course for beginners. That's the Eurocode 3 course, Reinforced Concrete Design with RFEM 6. And this is the Eurocode 3 course for the steel design with RFEM 6. The courses take about 2 or 3 hours. That depends on the course. You can interrupt the course anytime and continue when you have time again. There are different parts for the courses. That's no problem. Okay, that should be also all from my side. I thank you for your attention. Thanks to Clemens for the presentation. I wish all a nice rest of the day. Bye-bye.